Here's a spherical example. Let's find the flux of the vector field given by 7r through the sphere of radius 3 centered at the origin. Okay, so first let's think about the magnitude of the vector field. So the magnitude of F is equal to 7 times the magnitude of r. Okay, but if I'm always on the sphere of radius 3, then the magnitude of the position vector r is that radius 3, and so the magnitude of the vector field on the sphere is always 3 times 7, which is 21. So in particular, it's constant. The vector field is constant on this surface. Okay, second important observation is that this vector field points radially away from the origin. And so if you think about an orientation vector or a delta A vector, the angle between the blue vector, the vector field, and the red vector, the surface area vector, that angle is 0. So when we calculate F dot delta A, that's equal to the magnitude of F times the magnitude of delta A times the cosine of the angle between them. But if that angle is 0, then cosine of 0 is 1, and we simply get the magnitude of the vector field, which we know is constant, times the magnitude of delta A. Okay, so when we calculate the flux integral, this is simply going to be the magnitude of the vector field times the sum of the magnitudes of all the delta A vectors. And as we let delta A go to 0, this sum is simply the surface area of the sphere. So what we get is simply the magnitude of the vector field times the surface area of the sphere. So in this case, that's 21. That's the magnitude of the vector field. And the surface area of a sphere is 4 pi r squared. And here r is 3. So we get 21 times 4 is 84 pi, and if r is 3, r squared is 9. And the flux is then 756 pi. So again, let me point out that the important ingredients here. This vector field was constant on the surface, and the angle between the vector field and the area vector was always 0, which made things very nice. Next example is to find the flux of this somewhat ugly looking vector field, e to the x squared plus y squared I, through the disk of radius 2 in the xy or the yz plane, centered at the origin and oriented in the positive x direction. Okay, so here's the surface. It's still flat, and this is in the yz plane, and its orientation is in the positive x direction. So first, let's write down what dA is, or delta A. So I'm going to write dA. So notice that if I break the surface, the disk, into small pieces, into small rectangles, those rectangles have a y component and a z component. So I'm going to write that dy dz, and they're pointing in the positive x direction. So we're going to give that an I hat. Okay, so let's then think about what F dot dA looks like. So F dot dA is the vector field, E, so the x squared plus y squared I, dotted with dy dz I. So here there are no j or k components to deal with, and so the dot product simply turns out to be e to the x squared plus y squared dy dz. Okay, so that's essentially the integrand of the flux integral. So the flux integral turns into a double integral, and it's a double integral over the disk of e to the x squared plus y squared dy dz. So I just realized that I mistyped this problem. I think this problem would be a little difficult to deal with as it is. Difficult, or no, it would just be difficult. This x should have been a z. So throughout, that x is a z. And then notice that I just have y's and z's in this integral. There are no x's. And it's sort of begging to be turned into polar coordinates. So y squared plus z squared is going to be r squared. So we're going to do a double integral in polar coordinates. And again, y squared plus z squared is r squared. So I'm going to integrate e to the r squared, and then the dA piece becomes r dr d theta. Theta goes all the way around the circle, so it goes from 0 to 2 pi, and r goes from 0 out to the radius of the circle, which is 2. Okay, so then this is a fairly easy integral to evaluate with a simple substitution. W equals r squared. The limits of integration are constant. It's pretty straightforward, and you end up getting pi times e to the 4th minus 1. Okay, one more example, which initially looks a little strange, but turns out to be pretty easy. So we're going to find the flux integral of this vector field, 5i plus 5j plus 5k, through a disk of radius 3, and this disk is in the xy, or is in the plane y plus z, or x plus y plus z equals 1. Notice that it doesn't even tell me where this disk is in the plane, but it turns out that it doesn't matter. So first let's think about this plane. A normal vector to this plane is I plus j plus k. And so notice that the disk will have an orientation pointing in this direction. And further, notice that this normal vector is parallel to the force vector. So the angle theta between the vector field and the normal vector, again, is 0. So when we think about the magnitude of f times the magnitude of delta A times the cosine of the angle between them, as we've seen before, this simply turns out to be the magnitude of f times the magnitude of delta A times cosine of 0, which is 1. Okay, so this line integral turns out to be quite nice. It's simply going to be equal to the magnitude of the vector field times the area of the disk. Okay, so the magnitude of the vector field is easy enough to calculate. It's the square root of 25 plus 25 plus 25. And the disk, well, it's just a disk of radius 3, so its area is pi times r, which is 3 squared. So what do we get? We get the square root of 75 times pi times 9, and that's the flux.